We started this mini-series of videos by considering the fact that the derivative of the area of a circle, if the area is pi r squared, the derivative is 2 pi r. The derivative of the area of a circle looks like it's the circumference. In fact, it is the circumference, and we showed that's true. We promised that would lead us to some fundamental ideas about calculus, and indeed it did. We were led to the Fundamental Theorem of Calculus, which says that integration can be accomplished by doing the reverse of taking the derivative. Integration was a process of breaking things up into small pieces and then adding up the size of all those pieces. Pretty gnarly process, and it can be done by what we found out, it could be done by the easier, not terribly easy, but easier process of finding derivatives in reverse order. So we've met our objectives, but I want to do this one last video to clear up a loose end and also give an indication of where we're going next. The loose end has to do with this. Right after I pointed out that the derivative of the area of a circle is the circumference, I've also pointed out, just based on the formulas, that the derivative of the volume of a sphere, that's the formula for the volume of a sphere, the derivative of the volume of the sphere is the surface area. That's the formula for the surface area. You can see the derivative of r cubed, 3r squared, comes out to be that. But what I didn't show you, and I'll show you now, is why it turns out to be that. We'll look at the geometry. So here's a sphere. This dark blue thing is the original sphere. We're expanding the sphere. We're adding a little bit to the radius, that's the medium blue here, and that creates this new volume, the light blue. It's a shell. I've cut out a piece of the shell so we can see the original sphere. It's a shell around the original sphere. So the question is, when we're talking about the derivative of the volume, is how much volume gets added when you add just a little bit of radius? That is, what's the rate of change of the volume compared to the radius? And what I need to convince you of is this, that the change in the volume is pretty darn close to the surface area itself times this little bit of radius. You know, and I actually don't even have to convince you because you already know this. Let me show you how. I imagine you're probably watching this video in a room. If you're not, picture yourself in the room. And so let's suppose it's a rectangular room, that is the floor, all the walls, and the ceiling are all rectangles. How would you calculate the volume of this room? I think you all know you multiply the width of the floor times the length of the floor, and then times the height. Now the width of the floor times the length of the floor, that's the area of the floor. So we could say that the volume of your room is the surface area of the floor times the height. Now, let me draw just a picture of one of the walls of your room. How do we know that these two walls are parallel and make this in a rectangle? Well, you know, when someone builds the room, when they build the room you're in, they make sure that those walls are straight down. How do they do that? It might be they use a plumb line. A plumb line is something where you're hanging a weight at the end of the string and make sure that the walls go straight down so you actually have a rectangular wall. But think about this for a second. When you have a weight hanging at the end of the string, where does that really point? Yeah, it's straight down, but it points to the center of the earth. That's what the force of gravity does. It points to the center of the earth. And when you're pointing to the center of the earth, you're talking about a radius of a sphere. So this wall and this wall both point to the same place. They're not exactly parallel to each other. The point is, this room is so small compared to the giant sphere of the earth that whether these two walls point directly to the center of the earth or are completely parallel, it's virtually immeasurable. It doesn't matter. Now, are you not exactly convinced of that? Let's expand this thought a little bit. Suppose that next to you is a room just like the room you're in, and they have a common wall. Now, if someone was sitting in that room, they would also calculate the volume in that room by multiplying the area of the floor times the height. And your room, their room, they seem to be exactly the same and right next to each other. And picture 10 of these rooms, one after the other, or 100, or 1,000. I mean, anybody in any of the rooms looking at all the neighbor rooms would think they're all completely flat right next to each other. But imagine it going on for 10 miles, 1,000 miles, 6,000 miles. And what you wind up is a bunch of rooms kind of one after another. 6,000 miles is a quarter way around the earth. So the point is that each one of these rooms is so small that for them the surface of the earth is essentially flat and pointing in the direction of the center of the earth, which is what you do when you hang a plumb line, that these two lines are essentially parallel, even though clearly they're not. So each one of these people calculates the volume of their room as the area of the floor times the height. Altogether, when you do that, it's the surface area of this portion of the Earth times that little bit of radius. So that's my claim. You already know that this is true, that the change in the volume is pretty darn close to the surface area times the change in the radius. And what does that tell us? What we're looking for is the rate of change of the volume compared to the radius. So this is saying adding a little bit of radius, a tiny bit of radius, adds an amount of volume that's equal to the surface area times the radius, in other words, the derivative of the volume with respect to radius. How much additional volume is added per unit of additional radius? It's precisely the surface area. So this is very analogous to what happened with the circle. Now, we've done it for circles and spheres. Does it only work for round things? No, no, no. This is perfectly good for other things too. It's a little sneak preview. The next video you should watch is called "Why is the derivative of x cubed what it is and not something else?" And sneak preview, if we talk about a square and we expand the side a little bit, what does that do? That expands some extra area, and the area basically is this side plus that side. This is telling us that the derivative of the area, which is x squared, the derivative of x squared is 2x. Or for a cube, if I expand the side of a cube, it expands in 3 directions: towards us, off to this side, up towards the top, and how much extra volume is added? Basically, it's 3 slabs, and each one of those slabs has size x squared. So the derivative of x cubed is 3x squared. Look, this is just a sneak preview. If you didn't get that, please watch the video. Even if you did get it, watch the video because there's some other stuff in there that I think you'll find really interesting. And finally, the most general shape, in a way, is this. Suppose I draw a picture of a graph of a curve, any old curve, y equals f of x, and I ask this same question. How does the derivative of the area, or what is the derivative of the area? And again, by the derivative of the area, I mean, suppose I expand a little bit in this direction, in the x direction. I add a little bit in the x direction. That clearly is going to add some more area under the curve. How much is that area? Well, if this was a rectangle, it would just be the height times the width. It's clearly not a rectangle. But if delta x is very small, that same old thing we've been saying, if delta x is very, very small, it's awfully close to a rectangle. So it's delta x, the area of this yellow strip is delta x times this height. And what is this height? This is the graph of y equals f of x. That means that the height is exactly f of x right there. So we can say that the additional area is, the change in the area is f of x, the height, or roughly the height, times the width, delta x. So if we're comparing the area to the change in x, delta a over delta x, we get f of x. Take the limit as delta x goes to 0. The derivative of the area is, in fact, the function itself. That's pretty remarkable. Considering the graph of y equals f of x, the derivative of the area under this curve is f of x itself. And remember about the area under the curve. How do we calculate the area under the curve? We gave a hint about that in the last video. We break up the area into these little strips. Why? If we had just a plain old rectangle, a straight line across, we would calculate the area by multiplying the height times the width. But we don't have a single height here. The height keeps changing. So our trick is to divide the area up into these narrow strips. On each one of these strips, the height is not too different over the width of the strip. So we can multiply a representative height times the width, add them all up. That whole process we called integration. And we saw, even for a simple case, that was very complicated. But the good news is that you don't have to do that very complicated thing. You can instead do the derivative backwards. That's the fundamental theorem of calculus. The derivative of the integration process turns out to be the function itself. Derivatives and integration are the reverses of one another. In the previous video, I gave you that an example of how that worked for the circle. Here, I'm talking about the general case, giving you an idea, and we'll come back later and talk about that in more detail.